Well, a number of years ago, we started this idea at the KNIME user group that before we all went for a drink, and yes, I realize I'm standing between you and the alcohol, so we're going to keep this nice and tight and interesting, but I kept coming up with these ideas, and I go, oh, wow, why don't we? The first thing all the KNIME guys did is they go and say, Phil, no way. Well, I discovered my colleague in crime, Rosaria. She'd first tell me I was crazy, and then she'd come back the next day and go, you know what? I think we can do something around that. So this started 3 or 4 years ago, and let me just give you a little reminder of what it is we did, because it was actually a lot of fun at the time. One of the things we did, right in the beginning, there should be volume, should be sound. I'll turn it up this way. So that was the first thing we did. 3 or 4 years ago with Killian and Tobias, we went off and we combined networking and text mining. Hadn't been done up to then. Then Rosaria and I took on another topic, time series combined with machine learning. And we used some fantastic data that we got from the Irish energy trials. Lots and lots of fun. We were able to do things with KNIME that, quite personally, I'd never done before. The next one was last year. This was really hot, the Internet of Things, and it was a way of taking customer data and combining it with sensor data. And we had a lot of fun with that. How many people saw it last year? IoT. Okay, let's be a little honest. Every time we do this, we have a mission in mind. The mission is very clear. We're trying to make a white paper. We're not trying to create new science because the science is out there. What we're trying to do is pull it together, use public data, use KNIME workflows, package everything, and make that available to you so that you can download it. How many of you have downloaded one of those 4 papers in the past years? Yeah, they're good, aren't they? I mean, it's all there. You can play, you can change the data, you can start modifying things yourself, and that's the goal. So we came up today with an idea, and we thought, well, what are we going to do this year? I mean, last year's was soupy cool. We had fun. How do we top that? So we asked you, and you came up with a lot of different ideas, and you came up with topics. We kept being hammered with different topics that people would like to be seen. And one of the interesting things was, about all of these topics, they had a lot in common. And the commonality was this. A lot of the topics had to deal with prevention. Because if you're trying to prevent something bad from happening, whatever bad is, you actually want the ideal prevention would be to predict all failure before it occurs. So all of those topics I showed you, and it covers lots and lots of industries, actually covers that sort of thing. So the topic, as we've called it, is anomaly detection. Now, this is not outlier detection. This is anomaly detection, which is something a little bit different. Anomaly detection means that at some point, something really bad is going to happen. Yeah? And so you want to try to find out what's going on there. There's some definitions of anomaly detection, and I'd like to just cover that for a quick minute or two. First off, there's what we call supervised anomaly detection. And that's where we've already identified a group of patterns. And basically, we've been able to label those patterns and actually do modeling around them. To be honest, the vast majority of examples of anomaly detection on the internet right now that you can get from anybody else in the world is this right here. It's just a classification problem. Where's Dean? Dean, if I say anything wrong, you just hit me, okay? But, I mean, a lot of people are labeling it this way. Hey, we could do this. We do this every day. Okay. So the interesting thing about this, though, is this is a second topic. It's called static unsupervised anomaly detection. And once again, there's a couple of things that are common there. In this case, there's a number of different labeled patterns, and we're trying to find out when something fits and doesn't fit those patterns. But in both these cases, we're looking at existing patterns. And to be honest, quite frankly, an awful lot of the machine learning techniques that we all use every day apply there. So in this case, KNIME already has really good examples. Yeah? We don't call them anomaly detection, but we have them. So we've got a little bit of work, Rosaria and I, to take a couple of our examples and give it the right new labels. But there is a topic that's really hot. It's called dynamic unsupervised anomaly detection. And what's that mean? This means that maybe some measure over time starts to change. And there can be some sort of accumulation of this so that there's some sort of catastrophic event that happens. And of course, what we're trying to do is we're trying to get those really, really, really early indicators. The key here is there's never going to be a pattern, an absolute pattern. There's just some things that are going to change. It's not pattern-based, and it's usually done over time. So this is actually, in my opinion, what the IoT is really about. It's not just about a sensor from A to B. It's about all of these things that cycle through time, and you have to do that. There are lots and lots of examples, and they're all about cycles, motors, turbines, engines, the way a heartbeat, the way fluid goes through a process. Believe me, I'm a chemical engineer. Even network analysis, they're all examples of circular things. Now that's fun. Why is that fun? Well, back in the 1830s, there was a gentleman named Joseph Fourier. I'm pronouncing it wrong because it's French. He actually came up with the concept of the Fourier transformation. Who knows about the Fourier transformation? Isn't that great? I don't have to explain it. If you ever need to explain it to somebody who doesn't know, use this wonderful graph here because it's the fastest way to say we take everything having to do with this cycle, how big, how fast, where to start, and we convert it into a waveform. Isn't that the simplest way to understand this? I took a whole semester before I understood it. With that graph, you understand it in about 20 seconds. So that was fun, and that's where I got the music idea from. This circular, right? So we're talking about circular. We're going to go in there, and all of a sudden, we're going to have a problem because it goes down. Now there's a problem. There is a major problem with all of this, and the major problem is the following. Of all the areas we've ever looked at with KNIME, I have to do this manually to turn this thing off. There's no public data. For this particular problem, we have spent probably, or I've spent probably 6 months looking for public data. And you know what we like to do at KNIME. We like to package it all so you can download it and try it yourself. There was no public data, and we were getting really desperate. There's over 200 academic papers on this, and everyone says, look at my cool results, but I can't share the data with you because it's proprietary. Until now. What I'd like to do is talk very briefly about data that we've been given. It's about a motor. We don't know what kind of motor, and we don't care. 28 time series, 28 sensors, 8 different parts of a particular engine, lots and lots of information. What we're going to do is show you KNIME in action. We're going to go through some different pieces. I'm going to hand over to Rosaria. As all of you know, do not give Phil the KNIME bazooka. Give it to Rosaria. She's going to show you some very interesting things we did with the data. Rosaria.
Can you give me the point? Yeah. Okay, so let's see how this works. Doesn't work. Yeah. Okay, so we started with the data. As he said, those are time series that come from different signals. They arrived to us already after the fast Fourier transform was applied. There is only one motor breakdown episode in this data, and it's on July 21st, 2008. So we have a lot of supposedly normal data when the engine was working, and we are trying to predict that the engine is going to break before it actually breaks, so before the whole thing goes completely out of control. The engine, the breakdown is visible only from some sensors and only in some frequency bands. And the engine was substituted after the breakdown, and after that, of course, everything was new and everything was working again. Okay, so once we have the data, where do we start from? There is the usual pre-processing of the data, the cleaning, the conversion from the string to the date time, because we need date time objects. But the biggest problem was actually to bin the time series in terms of frequencies and in terms of time, right? Because the measures were taken at different times for different for different sensors. They came out at different frequencies, so at the end we were supposed to run some binning. That's what the numeric binner does, and the pivoting then builds a matrix where I have days on one side, frequency bins on the other side, and the average of the spectral amplitude as the measure. So this is what the pivoting node was doing. So even I have like 1, 2, 3 measures per each day for each sensor of the motor. So I put all of them in the same day bin. I define these frequency bins so that they are all 100 hertz large, and they cover the frequency between 0 and a bit more than 1,200 hertz. What is calculated inside is the average spectral amplitudes of the measures that end up in this bin. The second problem in all these measures is that I have, they were taken at different times, and some of these sensors, they have started working later, or they have they have times where somehow the measure didn't show up. I don't know why. So the whole problem is to do some time alignment with all these different measures. So the first thing that I did is an outer join on all the column values. The outer join produces a matrix like that, produces a data table like that, which has, if I join on the date, I'm going to have a number of missing values for the table that doesn't have this particular joining key. So I have to merge these two parts of the dates that were present in one table and not in the other one. So to do that, I use the column merger. The column merger is a node that is not very famous, but actually does this job very well of merging two columns and substituting the missing values with the existing values in the other column. Okay, so once I've done the time alignment, I can proceed with some data visualization. This is just a line plot, and you can see where the motor breaks. So here it's very clear where it breaks. Here you don't see that much. Maybe if you enlarge the scale, I don't know, if you do something, you can see something more, but actually in this particular frequency band, the 0-100 hertz, you don't see that much. You can see that that's the old motor piece, and that's the new motor piece. The new motor piece seems to work much better, at least in this frequency band. But what we have is this part here to train a model to predict that something bad is going to happen. Okay? Okay. So let's see how we do it. That's the same situation, but visualized in terms of with a heat map. So we use a heat map. Here we have the time. So the time goes from the 1st of January 2007 until, I think it's August 2009. And you can see that in some of the frequency bands for this particular signal, you can clearly see, when the breakdown happens. It's not that in the other ones it doesn't happen, only that it's not as clearly marked. Probably you can see it, but you have to announce it a bit more. Okay. You can also do a scatter plot. In the scatter plot here, I've done some thinking, and I've divided my time in 3 parts. The first part is the very beginning, January 1st, 2007, August 31st, 2007, when supposedly the engine was still working properly. Then there is this pre-breakdown time window between the September 1st and the July 21st. The July 21st is the day when the engine breaks. And then there is the time with the new motor. Okay, so if you run a scatter plot, then you can see that sometimes, and especially in some of the scatter plots, here we have the 500, 600 hertz frequency band versus the 200, 300 hertz. And here you can see clearly when the signal wanders around, and at the end it leads to the breakdown of the engine. So the difference between the previous, here I visualize all possible data, so it's the whole time. And this plot here is that here I've done some thinking and I've split my time in 3 time windows. Okay. I can also use some correlation maps. This one is an autocorrelation map, so it's the correlation of the current value of a signal, of a sensor signal in a particular frequency band with respect to its 10 past values. And this one is, sorry. And this one is for, in the very beginning, the first time period that I've used for the scatter plot, and this one is for the time window that precedes the breakdown of the engine. So you can see that the correlation properties are changing. Can we use that to do some kind of a prediction for something we have never seen? I don't know, but they are changing. Here it's the same, but instead of running the correlation of one current value with its past, we are running the correlation of each value on all the frequency bands. So instead of doing the correlation over time, we do the correlation over frequencies. And we calculate the correlation again on these 2 different time windows. And even here we see that there is a slight difference, some difference in the calculation of the correlation map at the very beginning and in the time that gets closer to the breakdown point. Again, can I use this difference in correlation? I don't know, but that's what we see here. So let's move to the data analytics. So we don't have a class here that we can say this is what happens when it goes wrong. We don't have a class of anomalies. We don't have a class that we can put in a decision tree and then we train the decision tree and we say that's normal, that's not normal. We have only what's normal. And then at some point, this normal is not normal anymore. So what we want to do in this kind of analysis is the only thing that we can do in this kind of analysis, we have no choice, is to define what's normal and then to train a model to reproduce or to predict what's normal. The idea is that if the model is not fed with normal data, with properly working data, then the model is going to fail. It's not going to perform well. Based on the failure of the model, we might get some conclusions that things are not working properly as they used to do when we train the model. So that's more or less the idea behind this kind of anomaly detection. There are many ways of doing that, and they are mainly related to how you train your model about the normal situation, about things working properly. As I said, we only have normal measures, and we need to train a machine learning algorithm to predict, to classify, to cluster, whatever the model is doing, those normal patterns. And then when the model is not performing well anymore, that means that the model is not in the situation it was trained for, so it's not in the normal situation, in the working properly situation. Okay, so you remember I've divided the time in these 3 time windows. The first time window is when things are working properly, the normal situation, and that's what I'm going to use as my training set. Then I have a time window here that I use to see if there is any sign that something wrong is going to happen. That's what I call the window for predictive maintenance. Here I don't train a model. I apply the model that I have trained before, and then when the model that I have trained before here gives me some uncertainty or tells me that it's not able to do what it was trained to do, then I started wondering if this is maybe an alarming situation. And then there is the last window, but this one I'm not going to consider much because things here are working properly, the engine is new, everything works fine. Okay, so training what's normal, we can do it in many ways. I'm going to show you one way, Iris after me is going to show you another way. One way that I've used is using the time series prediction. Time series prediction means that I move along time, I feed my model with the past values, and I train my model to predict the current value. That's what the time series prediction does. In particular, I used, so for each frequency band, for each sensor placed on different location of the engine, I have been training a linear autoregressive model using 10 samples in the past, no seasonality, because I mean that's a motor, so in theory there is no seasonality. And at the end, for the whole frequency band, sensor signals, and location on the engine, I trained 595 autoregressive models. So this is what I have at the end of the training phase. I train them only on the training window, on the first, the initial window, time window that I have in my time series, and I used only that to train my model. Now, this is the meta node that performs the training, so I just give a few details. This is the leg column node that produces the 10 samples in the past with which I feed my linear regression. This is to extract the time window, only, as I said, only the first time window, the one that I associate with the training set. This is a missing value strategy. There are some missing values, as I said, in some of the time series, and I use the last value to replace the missing values in my time series. So those are just nodes that are useful if you want to deal with time series analysis. And then finally, in this meta node, in the linear regression, I train my linear regression learner with the past, with the famous 10 past samples, and I write my output into the APMML model. The whole thing is a loop on all the signals, on all the frequency bands, and on all the sensor signals that I get. The idea is that when I go into production and I perform the same kind of pre-processing on the time series, I end up, so here I'm analyzing a different time window. What I do, I search for the right model. That means the model that was trained on the same frequency band and on the same sensor signal. I apply this model to the current value, and I check the prediction that this model is doing. In theory, if the conditions are the same in which the model was trained, the model is going to respond well. That means it's going to give me an error that is similar to the error from the training set, or maybe as big as maximum twice the standard deviation or something like that. If the model acts in conditions that are very different from what was from the conditions in which it was trained, then it's not going to perform well. So we can see it here. Here we are in the phase when things work properly. So my model, the green line, responds relatively well. The original signal is the red line. I mean, they are close enough, and the error is more or less the same that it was during the training, in the training phase. However, when things change, we can see that the prediction and the original signal are very much different. The prediction error becomes bigger and bigger, and the poor model is not able to keep up with the changed condition. And that's exactly what I want to find. I want to find an error that tells me that my model is not working properly. Not working properly means that the conditions are changed. That might be an alarming situation. Okay. So, and this is how the two workflows that have been used. This is for training, the whole training part, and this one is for the production workflow. So here I read my data, I select the right model, I calculate some values that I need for my alarm detection, and then finally here I have the triggering of the alarm for my anomaly detection. Okay, so let's see how I calculate, once I have this prediction error, how I decide that this one is an alarming situation or not. So this is the prediction error. It's an absolute difference between the prediction value and the original value. So if this prediction error is greater than the average value plus a number of times the standard deviation, then I say it might be an alarm. This one gives me a series of spikes. A spike can be anything. Can be the spike because, I don't know, there was some electricity issue. There was some, I don't know, something happened. One spike doesn't have to trigger the whole series of mechanical checkups of the mechanical engine, right? Maybe I want to be a bit more conservative than that. So instead, I use that only as first level alarm. Then I define a second level alarm after applying a moving average on the series of spikes. A moving average basically smooths my series of spikes, and only if I have many spikes at the same time, or if I have a very persistent error, continuous persistent error, the moving average is going to give me a very high value. Otherwise, if I have only one spike and then all zero or close to zero measures, the one spike is going to be lost in the moving average. So that's what I do using this moving average. I would like you to notice that I use the moving average with the backward window, because of course I don't want to get a peek into the future, so that's the only window I'm allowed to use in this kind of analysis. Okay, and this is the result. This is the meta node that performs the second level alarm, and this is the result, the signal that comes out. So it's all zero when things proceed smoothly. It starts becoming, with a little peak here. The first peak that we see is on March 6, 2008. The breakdown happens on July 21st, 2008. But it's very small, so depending on how conservative I want to be, I can detect this first peak, or I can just overlook that. However, this second peak, much, much bigger, that's something I cannot overlook. And this happens on May 5th. So I still have, even if I'm not very conservative, I'm going to reach a point when I can't ignore the second level alarm. And when this is the same plot, but instead of using the line plot, I use a stack plot from R, but it's the same plot as before. And once you have, your second level alarm fires off, then you can decide how you want to proceed. And here goes back to Phil.
And I always get the fun on how are we going to proceed. So there's lots of different things we can do on the analytic portion, but I thought it might be fun. You heard a lot of things that we can do in KNIME. You heard a lot of great ways that KNIME can interact with the environment, with your other systems. And I thought it'd be fun to just pick up a couple. Let's say there's an alarm that's worth sending. The first thing, of course, we can do right now is we can go off and we can send an email with all the details to a particular maintenance person's handset or whatever, but we can do a lot more. Using the RESTful services, right now, we can actually go off and do things like start having a flashing light go on. When I was a chemical engineer, this was our #1 way of knowing that a signal had triggered and that we needed to know something. But you can even get better than that with KNIME. Using RESTful, I can actually call this, and it'll take a second. This is one of the loudest sirens in the world in England, and you can use a RESTful service to call it. I bet the neighbors really love it. But most important thing about this is you can actually do a RESTful service or using some of the other interface ways at KNIME to actually go in and turn the motor off. So there's lots and lots and lots of ways of executing. And if I take a look at this workflow, we could finish right here. And I could come in and we could start talking about all the different ways we could do. But we got to thinking and we thought, hang on, there's more we can do. So what I'd like to do is now take a look at one other topic that we could look at, and that's let's try to go off and do a pattern recognition. And so I'm going to turn over very quickly to Iris, who's going to show how you could very quickly show a pattern recognition on this same data. Iris. Oder Iris ist besser, oder? Okay. Iris is okay. Thank you.
Recognition. The main difference between what Rosaria was doing in her analysis and me is that I didn't look at the single series attributes, but I always looked at the whole spectrum. And my goal was to find patterns in the older time slots which are similar and unsimilar to the data we are seeing in the possible future. And how I do this is I first take a look at my data. And what you are seeing here, again, the red are the whole series, all of our features, the whole set. So one data point is red, refer to a single observation. Now I want to model something, and therefore, I need to find out what is normal. And I always use big windows, mostly from the start of the series until some more recent point to model my past data. And this is what I then define or assume what is normal for me. And now I, of course, want to learn when my anomaly is happening. And therefore, I need to find a second window which I'm testing for being the anomaly. And this is the second window you're seeing here in yellow. And the green line indicates the moment when we are able to detect the anomaly. So you will see that, of course, it always does take some time. But if we are at this point can already see the anomaly, we can directly react to it. And for just to give an example here, the past could be from January 2007 to August, and the anomaly, or what we want to check for an anomaly, from 2007 to 2008. So how can we now do this in KNIME? I have therefore two basic ideas realized. The first uses the idea of fuzzy clustering. A cluster generates patterns in your data or tries to find them. And the good thing about the fuzzy C means is that it doesn't only find the patterns, but it also says this is the pattern, but with only a certain probability, this data point does belong to this pattern as well. So I'm generating using the row splitter my window, and using the interval loop start, I'm generating a bigger window in each of my iterations. And so for the first iteration, I'm generating this window. Then I've clustered using the fuzzy C-means on the whole data, not only on the past and the current data set. And then I assume if my most recent data point are the anomaly, they should be in the outlier cluster. And therefore, I filtered them here in this part, so it's only the last 10. And then I'm checking if these last 10 data points have a high probability to be included in the noise cluster. And if this probability averaged over the 10 data point goes up, we should have found an anomaly. And actually, this works. You see here that this is a probability that this data point is the last one indicating the anomaly. And there is a strong rise starting somewhere already before April 14th, 2008, which is as well the start of our anomaly we wanted to detect. So we could have detected it even a few days earlier using this technique. The second approach is pretty simple, but simple and similar. Here we did use the new distances nodes. And we did again make the same assumption that we have a growing window and a smaller window at the end, and wanted to check if the smaller window at the end is our anomaly in the end. And therefore, we tested that the smaller window in the end, which is generated by the second row filter, has a pretty high similarity to everything we have seen before. So all data points we have seen before should be unsimilar or less similar to our most recent data points. And the output was pretty obvious. We again found the April 14, 2008 is the second point here. So we could have detected the anomaly even one day early on the 13th before it actually happens. And the end of the anomaly was the 21st of July, which ended also in the end of here. But at this plot, you maybe see that we also generated an outlier, which, at least for us, is not clear why. And at the very end, there is also an anomaly detected. Okay, this was it from my side for the pattern recognition, and I give back to Phil.
Okay, what's interesting about this, thank you very much, Iris. What's very interesting about all of this is this bit here in the, let's go back, forward, this bit here in the middle. Whether we use time series, whether we use pattern recognition. Just before we started, Dean shouted out 2 or 3 other things he'd like to try there in the middle. We don't care. yeah? If we get the data right, if we're handling the transformations, the Fourier transformations correctly, you can do an awful lot of KNIME. What's very interesting is with what we heard this morning with the PMML and the way we can build up PMMLs, et cetera, there's a lot of different things we can now do to join quite complex models coming from different locations and actually go through and apply them to our signal when we want to execute. Now, because I'm just a guy that likes to go out to the bleeding edge, I actually thought, okay, that's kind of cool. We're looking at IoT data, we're looking at sensor data, we're looking at cyclical data, we can handle all of that, but is there a new kind of data that we're not yet including here? And the answer is yes. It's this. Did you know that there's now a camera that can capture more than 4 trillion frames a second? What is a frame when you make an image? A frame is nothing but data. And when you can actually start doing this, what does it mean if we can start taking the images and possibly do something with it? Now, from Siemens, we don't have motor data, a camera shooting it. But you can imagine, just based on that example I said, what would happen if at the same time we had all the sensor data, we actually had image data? And that's where I wanted to wrap up for you, because this is absolutely fascinating. KNIME's image processing is really good, and the man who really understands it is Christian. So Christian, what could we do with motor data?
Thank you. So I want to explain to you how we can detect anomalies or defects on image data. In this case, we have 1,100 images, which were sponsored by Bosch in a challenge, like a data challenge and an image processing challenge in the year 2007. As you can see, the images have like a regular structure, and we want to detect anomalies. I don't know if you can see it pretty clear, but here, these guys are anomalies. They are different from the pattern you recognize on normal images. And for each and every image, we want to detect, is there an anomaly or not on the image? This is very handy if you, for example, imagine that a manual inspection of materials or something is pretty expensive, and if you can detect them automatically by a computer, this saves a lot of time and therefore money. So I composed a small workflow to do that. I didn't write a single line of code for that. I just used what's out there. And so actually you can directly download it and start playing with it. The first thing I do is I read in the images into KNIME. So I have a list of images, a table of images. And here, for example, is an image without an anomaly. In the second step, I calculate features for each and every pixel on the image. This is like, I have a look at the neighborhood of the image, of each pixel, and calculate features like mean, variance, standard deviation, etc., or texture features. So I find a numerical description for each and every pixel, okay? This is computationally expensive, and we work on a way faster version of it, but at the moment it's pretty slow now. So the next step is, I tagged the images, I annotated them. So I annotated some defects, which I know from images this is a defect, I annotated it, and I annotated images which are not a defect. You can do that in KNIME, it's easy. There's a node for it called the image annotator. I did that for 20 images and created my training data, okay? In the next step, I trained a model. Given the training data and given the features for each and every pixel, I could train a model. In this case, I used a random forest. To distinguish between defect pixels and non-defect pixels, okay? And additionally, I determined the average size of the defects which I marked. So I know it has a certain amount of pixel size, each defect. Okay, and now detecting defects is just applying the model per pixel in the end. So what I did is I take the model, and for each pixel I can determine a probability that this pixel belongs to a defect or not. The whiter the image is, the pixel is, the more likely it's a defect in this case. And as you can see, there are a lot of small things where the algorithm says, oh, this could be a defect, but there's one very dominant thing here, and actually this is a defect, and I want to detect this guy. So what I do is I cut away all pixels which have a low probability that these are defects, and then I detect connected likely pixels as follows. And here you see I have a lot of small patterns here, but I know the average size for each defect, and so I can prune and throw away all the small ones, and I just the big ones, the big defects are left in my image. For example, in this case, this was this defect. It was a true positive. In the end, what I end up with is for each and every image, I can give a status. Is the image OK, or is there a defect on the image? And I did that for 1,100 images, and it worked quite well. It was like 89 or something percentage of correct classification. All right.
So what's fascinating about images, thank you very much. Isn't that fascinating? I mean, it's not just in the life science area. We're actually applying this technology in KNIME to lots and lots and lots of different things. And this is one way that I feel that over the next coming months and years, we're going to be seeing an awful lot more in the imaging space because it delivers more fantastic data. And of course, with the cameras working the way they do now, being able to actually slice that up, you can actually get some fantastic things. Why are we doing this? At the end of the day, in KNIME, this is what we're trying to do. We're doing all of this to get a new column of input information that we can use in all of our modeling routines to actually come up with more accurate alarm sequences. So you can see what we've done here with the KNIME in action. We've gone through, we've actually read the data, we've gone through, done time series, pattern recognition, we've enriched with images, we've gone off and showed you a couple of different ways that you might want to pick up on the signals and execute on the signals. Of course, there's a lot more we could do over here, also with the likes of Cementis, who is here. As you can imagine, you can really do some cool things. Last thing I'm going to mention, because we ran out of time, there's a lot more we can do. Tobias was showing this morning all the different things you could do with the new big data extensions. There's a natural place for that there if your data gets too big. There's also a natural place for it there. We've also started thinking about how can we combine models, use random forests. Dean, you had another idea or two about what we could be doing here. So there's a lot more that we could do this. I want to finish with one last little story, though, and it's about text. I had the pleasure of talking to the Airbus people who are using KNIME. And interestingly enough, they're doing all the same sorts of things. But the interesting thing is, he was actually using the stuff that Kilian came up with, the text mining. How is he combining text mining with all of this anomaly detection about machines? They were reading the reports of the mechanics who were doing the upgrades on the machines, and they were discovering that those handwritten notes were one of the earliest indicators that there may be a problem later on. The machinist didn't actually say, there will be a problem, but based on the language that was coming in there, they were actually pulling that in. Once again, more columns of data, straight from KNIME, straight in to make our models even more powerful as we go forward. Isn't that fun? Yeah? All I can say at this point is, we had so much fun with this. Using all of this circular data, you can really see how you can combine KNIME in lots of different ways. As always, we promise that there will be a white paper and a download. If you need that early, please come and talk to either Rosaria or myself. We'll see if we can get you what you need right now. But this is a really hot topic, and I'm really looking forward to seeing your examples of this next year as we take a look at anomaly detection. And yes, that is the original video from 1964. Talk about images and capturing them. Thank you very much.